selected crystal, they don't all come this way, ended up with an energy resolution of 1.75%. Now, there's plenty of room for improvement. You see some areas of this crystal still produce poor energy resolution. This is you can't read the numbers, but the good energy resolution only comes from a portion of the crystal. The trick is going to be to learn why this portion of the crystal turned out to be much better performing than other parts of it. So that's still in the crystal growing science, which I tend to feel is more of an art than a science, and there's a lot to be learned still on how to grow these crystals. Yeah, here's the material that some of you here are familiar with, since again Dr. Amada's group has taken a look at thallium bromide. Again, a very high Z value with the thallium. So even thin detectors, a centimeter or so, is still quite an attractive gamma ray spectrometer. This material, unfortunately, is rather unstable at the present time. No one is quite sure why there are problems with what's called polarization of this material. That's an area under active research right now. Perhaps with additional research, we'll understand better why these detectors do not stabilize as well as they should. And in the future, this could be, in fact, quite a useful material as well. Also wide bandgap room temperature. Even in their present state of development, there are some interesting results. This is work from radiation monitoring devices in Massachusetts, where with a 1 centimeter thick thallium bromide detector are getting something like 2% energy resolution. And again, there ought to be a great deal of room for improvement here, since the statistical limit on energy resolution in these devices is down below 0.4 or 0.3%, something like that. So there's a big area that's open for potential improvement. So finally, I'd like to show another example of the use that can be made of this three-dimensional information provided by this wonderful ASIC readout. It provides many, many parallel readout channels so that you know where interactions occur within the volume of the detector. And this is going to be now radiation imaging. That is, finding out the direction from which the radiation, the gamma rays, originate. There's, of course, interest in that in medicine, in nuclear medicine, but also in other applications such as homeland security, where one is trying to see the object of interest and try to determine whether gamma rays are emerging from one particle or another. So this is a technique known as Compton imaging. I'm sure there are many of you in the audience familiar with this. It's an old technique, generally implemented using two detectors, both of which have energy and position capability. And for example, in gamma ray astronomy, many measurements have been made using two separate detectors of this sort, where the gamma ray scatters in the first and is totally absorbed in the second. If you know the position of interaction in both detectors and also the amount of energy deposited there, one can calculate this angle theta, which is the scattering angle, and therefore define a cone which can be back projected, and one knows then that the real source must lie on the surface of that cone. Well, doing this multiple times then, this is much like tomography, you get overlapping cones where the source really lies, and so after hundreds or thousands of these events, you have an image of the point of radiation. Well, this approach using two separate detectors is geometrically inefficient. There are two solid angles here, so the efficiency is very low. It makes much more sense to do it in one contiguous detector, where you have a much greater acceptance fraction. And now you get the same principle. You can again back project the cone, knowing three-dimensionally where the interactions occur inside a homogeneous detector. And here's an example of two-point sources being imaged on the surface of a sphere. This, now when you have a monolithic crystal, this is a 4-pi detector. It's looking in all directions at the same time. Not like the aperture, some other collimator device which has a narrow field of view. This is looking everywhere. And here you see on the surface of the sphere, where the detector is at the center of the sphere, you see the two-point sources. Here's just another example using different kinds of source reconstruction algorithms. One is simple back projection, much better borrowing techniques from tomography, where maximum likelihood techniques are now routine and equally applicable to this problem of counting imaging. This is an example in which the students decided to set up the detector. This is a single 2 cubic centimeter detector in the laboratory and measured the background spectrum. And then they singled out one of the lines, this bismuth 214, which is a daughter in the uranium-238 decay series. This comes about largely from the concrete that's in the laboratory, which has impurities in it, heavy impurities, including trace uranium. And this line comes from that. And they then did an image of the laboratory. And here you see it, it's laid out as a 360-degree panorama. From here to here is going around 360 degrees. Top and bottom are up 90 degrees and down 90 degrees. And here you have an image of where the background's coming from. Kind of, I think, somewhat of a unique picture. There aren't too many of these out there. But what you see, in fact, is the hotter areas are the nearby walls here, they're concrete. Over here are the windows where there is no concrete, and that's the blue area. And over here again, more wall material. Looking upwards, you see it's fairly cool, meaning it's a thin roof on the building. This is on the second floor, whereas looking downward, there's activity from the floor, because that also is concrete. Well, just to make sure we're not fooling ourselves with artifacts, the detector was then turned 90 degrees, and you see that the image shifted essentially 90 degrees to the right, as it should, so it looks like, in fact, it's real. This is a point source found accidentally because it was in the next door laboratory, and lo and behold, here is source turning up at the cesium energy, just because it was outside the cave and on a bench top, and by golly, turns out after this process of imaging. Well, this technology is being picked up by others. This is some work at Pacific Northwest Laboratory in the US, building a handheld detector based on an array of many of these three-dimensional detectors. Any one of these detectors has rather low efficiency. However, there's no reason they cannot be built up into more volumetric arrays. And here's an example of one approach to do that, using 18 of these cubes of CZT, coupled in each case with an output ASIC. And you can see this makes a compact package. And one of the advantages here of the ASIC readout is that, in fact, nearly all the mass of this sensor is the active CZT. Very little is passive material that can scatter and interfere with measurements. That is now being engineered into this kind of portable package that will hopefully undergo trials coming up in a few months. One of the big questions is availability of CZT, and that is certainly still a problem. There are not very many companies attempting to grow CZT. The recipes for growing CZT are closely held secrets by these companies, And one of the more promising